I'm Darren Llewellyn. Welcome to another episode of MyToolboxTV. Today we want to talk about magnetism. Magnetism is very important in electrical work. It's what makes a lot of things work. Transformers, motors, all kinds of things, even your doorbell at home. So let's take a closer look at magnetism. Let's talk about a simple bar magnet. A bar magnet, or any kind of magnet, has poles. A north pole and a south pole. And just like with atoms and current flow and the other fundamentals of electricity, opposites attract. Okay? North poles are attracted to south poles. Theoretically, on a magnet, and I don't know if anybody's ever seen this or not, and I'm sure not a physicist, there are what people call magnetic lines of force, or flux lines, coming out of a magnet like this. Okay? These magnetic lines of force are attracted by the opposing pole. Opposites attract. If you were to take another bar magnet, let's say just like this one, and put it right here, and put the north pole of the other magnet facing the south pole, they would attract. They would hold together. And you've all done this. You've all played with refrigerator magnets or other kind of magnets. When they stick together, you've put two opposing poles together. If you were to take the south pole of this bottom magnet and force it to the south pole of the other magnet, they will repel. Opposites attract, likes repel. So if you've ever put two magnets together and they flew apart, it's because you had matching poles facing each other. And it was always a fun game to see how high, right, when you were little, to see how high you could make that magnet go. So opposites attract and likes repel. Now let's take a look at an electromagnet. An electromagnet is generally made out of a coil of wire. And what happens when current flows through a conductor, through a wire, there's a magnetic field around that wire. If there's current flowing through this conductor right here, then there's a magnetic field around that wire. The more current, the more the field. Now, if you take that wire and put it in the form of a coil, all of those small magnetic fields will join together and make a large magnetic field. Okay? We'll make a large magnetic field. One end of this coil will be the north pole. One end will be the south pole. And there's rules on how to figure that out that are beyond the scope of what we're doing today. But there will be a north and a south pole. Another important fundamental of magnetism is if you've got a magnetic field, whether that magnetic field is created by an electromagnet or from a bar magnet or from whatever reason, if you pass a conductor through that magnetic field, the magnetic field will induce a potential, a voltage onto that conductor, and if it's a complete circuit, will cause current to flow. So a magnetic field can induce current into another conductor without physically contacting it. That's how transformers work. That's how three-phase motors, squirrel cage motors work. Lots of different things run that way. So magnetic fields are very useful. Now, a magnetic field, this coil like this has a couple names. You could call it an inductor or a reactor. One of the principles of an inductor is to oppose a change of current. It opposes any change of current. So if this is going, and it's DC, we'll say, so there's this magnetic field built up. If you take away the source, the coil wants to keep the current going. So it opposes a change in current. The way it keeps the current going is that magnetic field, when shut off, will collapse. When it collapses, that collapsing magnetic field will induce current into the very coils that created it to try to keep the current going. If the magnetic field is turned off, and you apply voltage, you apply a source to get current moving, this coil will oppose a change in current. It will try to stop the current from coming. The same current that just a while ago it was trying to keep going, now it's trying to stop it from starting. So it opposes any change in current. We all know people that way, that oppose change, that are always against change. Well, that's the inductor. And when it does that, when you turn the source on, the magnetic field that's building up opposes and induces current into the very coil that it created, or that created it, and tries to stop the current. Of course, it can't. Eventually, the current comes and the magnetic field gets built up. This property of inductance, this property of a magnetic field, electromagnet, has lots of reasons why we use inductors and transformers and motors and all kinds of things. Let's take a closer look at how we can get mechanical motion out of an electromagnet. Let's look at an electromagnet being used to create mechanical motion. You'll probably never guess this, but this is your doorbell at home. Okay? This is your button on your front door. This is inside the actual housing where the noise comes from. This is the AC source, which in most homes this is going to be about a 13-volt transformer connected to a 120-volt source using magnetism to get the lower voltage, because you don't want 120 volts hooked up to your little button outside. When you push your doorbell and close this switch, this becomes electromagnet. Okay? It's a magnet. This is the plunger that's going to make the noise for your doorbell. When this becomes electromagnet, this metal plunger, this iron plunger, will be pulled up into the coil. When it pulls up into the coil, it's got a little rubber tip on it. It will hit this bar. It will hit this bar up here, and that's the bar that makes the tone, the dong for your doorbell. Sometimes doorbells are really cool. They're fancy. They've got two tones. There's another bar at the bottom, so when the plunger falls back down, it's got a little spring action thing on it. It hits this bottom one and makes the other sound. So it's electromagnet. It's just a small, it's called a solenoid. When you're using electromagnet in this function, it's called a solenoid. It's got lots of different uses. Here we're causing a doorbell to ring, and all we're doing is when we close this button, current flows through this circuit, causing a magnetic field. Plunger comes up and hits the bar that makes the sound, and then it falls back down. This could also be, this plunger could be connected to a valve. Maybe it's you've heard the term solenoid valve. A solenoid valve, this could be a valve thing down here with spools for hydraulics or water flow or all kinds of things. It could also be connected into a relay. Let's take a look at a relay right now. So here's a situation where you've got a coil, and maybe this coil is hooked to an AC source. And so current's flowing through this coil, making an electromagnet. Remember, it's AC, so it'll be going different directions. When it does, this plunger right here, this armature, part of the device, pulls down into the magnetic field, closing this contact. What's really cool about this is this. You could put a circuit up here. Here's a battery with a light bulb and completing the circuit. Check out how it's going to work. This AC source could be 120 volts AC. And this could be a 9-volt battery. So the 120 volts pulls in the coil, pulls down the armature, closes these contacts right here, completes the circuit up here, and this light bulb's turned on. Now, it wouldn't be very often you'd have 120 volts controlling 9 volts. That'd be kind of silly. But you could easily have 120 volts controlling 480 volts, and this be a motor circuit instead of a light bulb. So relays, contactors, those sorts of things can also be, are made using electromagnetism, a solenoid. using basically electromagnet to cause mechanical motion. Thanks for tuning in to another episode of My Toolbox TV. Today we talked about magnetism. Hopefully it was helpful for you. Come back, come often. We'll be talking about a lot of other things. See you next time.